Ever wonder how your brain makes decisions even when you don't have all the facts? Like, what if we could build a machine that thinks like that? Today, we're going deep with excerpts from E.T. Jaynes' book, Probability Theory, The Logic of Science. And we're going to explore just that.
It's fascinating how this book dives into how probability theory can actually model our decision-making process, especially when we're dealing with incomplete information.
Which is pretty much all the time, right? Let's be honest. Who has all the facts before making a decision?
Exactly. And this is where probability theory gets interesting. It's not just about randomness, It's about logic. It's about inference under uncertainty. It's about how we can figure out the most plausible explanation given what we do know.
So if we can understand how our brains make those judgments with limited data, then we're one step closer to building machines that can do the same, which is exactly what you're interested in with AI.
Absolutely. And Jaynes even suggests that we could build a machine that uses these principles. Imagine software that can sift through mountains of data, like a superpowered detective, and picks out the most probable explanations.
So it's not just about building a machine that can crunch numbers, it's about building a machine that can think.
Precisely. And that's what's so exciting about the development of AI and machine learning. They rely heavily on these principles of probabilistic reasoning.
Now, Jaynes really gets into the weeds with this, arguing that using real numbers to represent these degrees of plausibility is crucial for a robust theory. I'll admit, some of this stuff went over my head, but
Yeah, it can get pretty dense. Some have even argued for using qualitative comparisons instead of numbers. But what's important is that the core idea shines through, using logic and inference to make sense of uncertainty, regardless of the specifics.
So even if the exact methods differ, the fundamental idea holds true.
Exactly. Now, you're going to see some specific notation used by Jaynes. He uses a capital P for propositions and other symbols for numerical values. It's kind of like learning a new language. Once you grasp the vocabulary, you can follow the conversation.
And speaking of vocabulary, he also keeps mentioning this finite sets policy. What's that all about?
That's a good question. It might seem abstract at first, but it's really crucial when you're dealing with real-world data. You can't measure something infinitely precisely, right? So this finite sets policy helps us avoid getting tripped up by theoretical infinities.
So it's like saying, hey, infinity is cool and all, but in the real world, we have to deal with concrete measurements and boundaries.
Exactly. And to illustrate these core concepts, Jaynes brings up the classic example of the urn problem.
Now, I know you're probably thinking, urn problem sounds a bit boring, but trust me, these classic examples are surprisingly powerful for understanding how probability works in the real world. And they even pose some tricky brain teasers that I bet you'll want to try out.
They really do help visualize things. Imagine an urn filled with colored balls. You reach in and pull out a ball. Maybe put it back in, maybe you don't. This helps us understand how probabilities change based on previous events, or what we call sampling without replacement.
Okay, that makes sense. It's like figuring out the odds of drawing a specific card from a deck after you've already drawn a few.
Precisely. Jaynes uses specific examples, like calculating the probability of drawing certain colored balls multiple times in a row. And here's where it gets fun. He even throws in a couple of exercises to test your understanding. For instance, what are the odds of getting at least one ball of each color when you're drawing from an urn with multiple colors?
Ooh, that's a good one. It's making me think.
And that's the point. Even within this structured framework of probability theory, your intuition and common sense still play a role. It's not just about blindly applying formulas.
It's like having the tools and the knowledge, but also needing that human spark to apply them effectively.
Exactly. And as we move beyond these urn problems, we'll see how probability theory can help us assess hypotheses based on real-world observations, not just colored balls.
So instead of wondering about the color of the next ball, we're looking at data and trying to figure out what it tells us about the underlying causes. Kind of like being a data detective.
That's a great analogy. And remember, it's not always about finding a direct cause and effect relationship. The key is the logical connection between a hypothesis and the data we observe. Does the data support the hypothesis, or does it point us in a different direction? That's what probability theory helps us figure out.
It's about asking, given what I know, what's the most likely explanation?
Precisely. And this brings us to a crucial concept: independence. Now, you might think independence is pretty straightforward, but there's more to it than meets the eye.
Okay, let's unpack this. What kind of nuance are we talking about here?
Well, when we talk about independence in probability, we have to be careful to distinguish between two types: logical and causal. Logical independence means that the truth of one proposition doesn't affect the truth of another, while causal independence refers to actual physical influence in the real world.
Oh, okay. So, like, just because two things happen together, that doesn't mean that one causes the other. There might be some hidden connection, or it could just be a coincidence.
Exactly. And here's where it gets tricky, especially when you're thinking about building AI systems. If you assume independence when it doesn't actually hold, then you can get some pretty serious errors in your conclusions.
Yeah, that makes sense. It's like building a robot detective that just assumes everyone at a crime scene is unrelated when, in fact, they're all part of a complex web of relationships. You're going to miss some crucial clues.
Precisely. Jaynes actually uses a specific equation to illustrate this point. And he even points to some of the controversy surrounding this issue in artificial intelligence. It really highlights how important it is to carefully apply probability theory and not jump to conclusions.
So it's like any powerful tool, you need to know how to use it properly to get accurate results.
Absolutely. And to really drive this point home, Jaynes shares a fascinating anecdote about Mrs. Stewart's ESP experiment. The data seems to overwhelmingly support her psychic abilities, but,
Hold on, ESP. Are we going full X-Files here?
well, not quite. But it's a great example of how even when the data looks really impressive, it can be misleading if you're using the wrong tools. In this case, the normal approximation, which is a common statistical method, dramatically overestimates the likelihood of her results.
Oh, so it's like using a ruler to try and measure the distance to the moon. The wrong tool for the job.
Exactly. And this underscores a crucial point. Extraordinary claims require extraordinary evidence, and we need to be really careful to evaluate all the possible explanations, not just the ones that seem most obvious.
It's always good to be a little bit skeptical, even when you're faced with impressive-looking data. So how does probability theory help us avoid these kinds of pitfalls?
Well, that's where Bayes' theorem comes in. It's a really powerful tool for updating our beliefs based on new evidence, even when that evidence is uncertain.
Okay, Bayes' theorem.
Yeah.
This is one of those concepts that seems so simple, but then also really mind-boggling at the same time. How does this actually work in practice?
Well, Jaynes provides a scenario where two people are trying to evaluate the safety of a new drug based on the testimony of a third party who isn't exactly known for their reliability.
So, like getting a recommendation from someone whose judgment you're not quite sure of, do you trust them or do you go with your gut?
Exactly. And how their opinions shift, either coming closer together or diverging further apart, perfectly illustrates how Bayes' theorem works. It allows us to take in that new information, even if it's not rock solid, and adjust our beliefs accordingly.
Okay. It's like adding a new piece to a puzzle. Even if it doesn't fit perfectly, it can still give you a better understanding of the overall picture.
Precisely. But Jaynes also acknowledges that applying Bayes' theorem in a strictly quantitative way to evaluate complex scientific theories can be tricky. It's not always about the math. Sometimes it's about coming up with the right questions and hypotheses in the first place.
So even with all the computational power in the world, if you're asking the wrong questions, you're not going to get very meaningful answers.
Exactly. And this brings us to another important concept that often gets overlooked. It's the idea of hidden information in parameter estimation.
Before we get into that, can you just remind me what parameter estimation is all about?
Sure. It's about using data to try to infer the values of unknown parameters that describe a system. For example, think about those colored balls in the urn again. If you only see a few balls that have been drawn out, can you estimate how many of each color are actually inside the urn?
So it's like trying to figure out the ingredients of a cake just by tasting a small slice.
Exactly. And what's fascinating is that even data that we might consider irrelevant or unused can actually contain a lot of information that subtly influences our conclusions. And Bayes' theorem automatically takes this into account, even if we don't consciously realize it.
It's like realizing that even the crumbs on the plate can actually tell you something about the texture of the cake, even if you didn't pay attention to them before.
Precisely. Now, let's shift gears a bit and tackle a topic that I think you might find particularly interesting given your interest in AI. And that is the concept of randomness. We'll use something that everyone's familiar with as our case study, coin tossing.
Ah, coin tossing, the ultimate symbol of chance. But are you telling me it's not as random as we think?
You got it. Jaynes really challenges this notion that coin tosses are truly random events. He argues that factors like the initial conditions of the coin and the way that you flip it can actually have a significant influence on the outcome.
Wait, so you're saying like the way I flip the coin matters? That's blowing my mind a little bit.
It can be counterintuitive, but think about it. The physics of the flip, the force you use, the angle, the air resistance, all of that comes into play. It's not just purely luck. And he even provides some examples of specific techniques that people have used to create a bias so that they can get predictable results.
Oh, wow. So it's like a magician's sleight of hand. It looks like magic, but it's actually carefully controlled movements, creating this illusion of something impossible.
Exactly. And there's this famous observation by Poincaré that even tiny, tiny changes in the initial conditions of a coin toss can drastically alter the probability of heads or tails. It all comes down to these intricate laws of physics that are governing the toss.
It's like that idea that maybe a butterfly flapping its wings in Brazil could actually lead to a hurricane in Florida, like these tiny little actions having this huge impact down the line.
Precisely. And it challenges us to think about how we define fairness in a coin toss. If we try to define it based on the frequency of heads, we end up in a little bit of a circular argument. It's a really fascinating exploration of how probability intersects with the physical world.
It makes you wonder if the concept of randomness is really more about our own limited understanding than some inherent unpredictability in the universe.
That's a great point. And Jaynes takes this critique of randomness a step further and applies it to the mind-bending world of quantum mechanics.
Okay, quantum mechanics, the place where things can be in multiple states at once. Now we're really getting into the weird stuff.
Yeah, it is weird, but also incredibly fascinating. But Jaynes argues that even though quantum mechanics seems to embrace probability as like a fundamental property of nature, this interpretation can lead to some logical inconsistencies.
So are you saying that it's not really random after all?
Well, Jaynes proposes that it might be another case of what he calls the mind projection fallacy. We see the limits of our own knowledge, and we kind of project that onto the universe, assuming that it must be inherently random. But maybe there's just a deeper level of complexity that we haven't fully grasped yet.
It's like saying, I don't understand how it works, so it must be magic, when in reality, there's probably a perfectly logical, although incredibly complex explanation.
Exactly.
Yeah.
Now, to really understand where Jaynes is coming from, it's helpful to look back at the historical development of probability theory.
Okay, so let's take a little trip back in time. Who are some of the key figures that shaped this field?
Well, we have to start with giants, like Daniel Bernoulli and Laplace. They made some truly groundbreaking contributions. But even they faced resistance and skepticism from their contemporaries.
That's often the case with new ideas, right? They challenge the status quo, and not everyone's quite ready to embrace that. What kind of ideas were they pushing?
Well, Bernoulli tackled the famous St. Petersburg paradox. It's a thought experiment about a coin toss game, where you could theoretically win an infinite amount of money.
That sounds like a pretty good deal. What's the catch?
Well, the catch is that most people wouldn't actually be willing to pay very much to play, even though the potential winnings are unlimited. And this led Bernoulli to introduce the concept of utility, which considers the subjective value that we place on different outcomes.
Oh, so it's not just about the raw numbers, it's about how we actually feel about those outcomes.
Exactly. A dollar isn't always worth a dollar. It depends on your individual circumstances and your preferences. And then, of course, there's Bayes, whose theorem revolutionized the way we think about updating beliefs based on new evidence.
Bayes' theorem, the cornerstone of so much of modern statistics and machine learning. It's amazing how these early ideas still have such a profound impact on how we understand the world.
It really is.
Yeah.
And Jaynes explores the debate between the two main approaches to probability that emerged from these early ideas. That is, the frequentist and the Bayesian perspectives.
Okay, remind me again, what's the main difference between those two?
Sure. Well, frequentists view probability as a long-run frequency of events based on repeated observations. Think of it like flipping a coin a million times. The frequency of heads should approach 50%.
Right, that makes sense. So how do Bayesians see it?
Well, Bayesians see probability as a measure of belief, and that belief can be updated as we get new information. So a Bayesian might say, based on what I know about this specific coin and how it's being tossed, I believe the probability of heads on the next flip is 60%.
So it's not just about that long-term average, it's about taking into account all the specific information that you have at hand.
Exactly. And Jaynes delves into the strengths and weaknesses of both approaches, showing how they can be complementary in some situations while diverging in others.
It's like having these different lenses to view the world through, each offering a unique perspective, and sometimes you need to use both to get the full picture.
Well said. And this historical context really sets the stage for a deeper dive into some of the more advanced concepts in probability theory.
Okay, I'm ready to go deeper. What's next on this journey?
Well, let's talk about entropy. I know it sounds kind of intimidating, but it's a fascinating concept that links probability theory to thermodynamics.
Entropy, the measure of disorder, right? I remember struggling with that back in physics class.
Yeah. But what's fascinating is that Entropy can also be understood as a measure of uncertainty in probability distributions.
So instead of measuring the randomness of molecules in a gas, we're measuring the randomness of our beliefs.
Exactly. A high entropy distribution basically means that we have a lot of uncertainty about the outcome, while a low entropy distribution means we're more certain.
It's like comparing a messy room to a tidy one. The messy room has higher entropy because there are more possible arrangements for all the objects, while the tidy room has lower entropy because it's more organized.
That's a great analogy. And this leads us to the principle of maximum entropy, which is a really powerful tool for assigning probabilities when we have limited information.
So instead of just kind of guessing, we have this principled way to quantify our uncertainty. I like that.
Right. It basically states that we should choose the probability distribution that maximizes entropy while still being consistent with whatever we already know.
It's like saying, given what I know, what's the most honest way to represent my ignorance?
Precisely. And what's remarkable is that the maximum entropy distribution often corresponds to the frequency distribution that can be realized in the greatest number of ways. And this links probability to the field of combinatorics and helps explain why certain distributions, like the Gaussian or normal distribution, are so prevalent in nature.
So the most probable outcome is often the one that has the most ways of happening. It's all about possibilities.
Exactly. And the principle of maximum entropy has applications that go far beyond just coin tosses and dice rolls. It's used in physics, in chemistry, in economics, all sorts of fields to model complex systems and make predictions.
It's amazing how this seemingly abstract concept can have such wide-ranging practical applications.
It really is. And as we go deeper into Jaynes' work, you'll see how these core concepts of probability, randomness, and uncertainty connect to even more fascinating ideas.
Okay, I'm ready for more. What else has Jaynes got up his sleeve?
It really is mind-blowing stuff, but that's what's so great about Jaynes' work. It challenges us to think deeply about these fundamental questions and to really see those connections between what seem like totally different fields.
Absolutely. So where do we go from here? What other rabbit holes does Jaynes lead us down?
Well, one of the most fascinating aspects of his work, I think, is how he applies probability theory to the problem of induction. You know, the classic philosophical puzzle of how we can draw these general conclusions from limited observations.
Right, like how do we know the sun will rise tomorrow just because it's risen every day in the past?
Exactly. It seems like common sense, but philosophers have been grappling with this logic of induction for centuries and centuries. And Jaynes argues that probability theory actually gives us a framework for understanding how induction works.
Oh, so it's not just about making educated guesses. There's an actual mathematical foundation for it.
That's right. And Jaynes shows how Bayes' theorem can be used to update our beliefs about the world as we gather more evidence.
Oh, so like each time we see the sun rise, we become a little bit more certain that it will rise again tomorrow.
Exactly. And he connects this to the idea of exchangeability, which we touched on earlier. Remember, it's this idea that the order of observations doesn't actually matter when we're trying to infer probabilities.
Right, like with those colored balls in the urn, it didn't matter what order we drew them in, the probabilities stayed the same.
Precisely.
Yeah.
And Jaynes argues that this concept of exchangeability is really crucial for understanding how induction works. It allows us to take our limited experience and generalize from that to make predictions about future events.
So it's like saying, well, if I've seen like 1,000 white swans and I've never seen a black swan, then it's pretty reasonable for me to believe that most swans are white.
Yeah, that's a good example.
Yeah.
Of course, as we know, black swans do exist, so induction is never foolproof. But Jaynes shows us how probability theory provides a way to quantify our uncertainty and make these rational inferences based on the evidence that we do have.
It's all starting to click into place now. So probability theory isn't just about calculating the odds. It's like this powerful tool for understanding how we learn and make sense of the world around us.
Exactly. And this brings us to another key theme in Jaynes' work, the importance of prior information.
Okay, we've talked about priors before, but why are they so important?
Well, Jaynes argues that we can't actually make any inferences about the world without starting with some prior beliefs. Even something as simple as observing the outcome of a coin toss requires us to have some prior belief about whether that coin is fair or not.
So we can't just approach the world with a completely blank slate. We always bring our past experiences and assumptions to the table.
That's right. And he emphasizes that our priors should be based on all the relevant information that we have, not just our own personal opinions or biases.
So it's about trying to be as objective as possible, even though we can never completely eliminate subjectivity.
Exactly. And this leads Jaynes to develop some really interesting and sometimes controversial ideas about how we should choose our priors. He argues that in cases where we have very limited prior information, we should use what's called the principle of maximum entropy.
Oh, yeah, we talked about that earlier. It's about choosing the probability distribution that basically maximizes our uncertainty, given what we do know.
That's right. And Jaynes shows how this principle can be used to derive some surprising and really powerful results in a whole range of fields, from physics and statistics to economics and even artificial intelligence.
Wow. It's incredible how these core ideas from probability theory keep branching out and connecting to so many different areas of knowledge.
It really is. And this interconnectivity is one of the things that makes Jaynes' work so fascinating and so influential.
Okay, so we've covered a lot of ground here. What would you say are the key takeaways from our deep dive into Jaynes' work?
Well, I think the most important message is that probability theory is not just about randomness or chance. It's a powerful system of logic that can be applied to a huge range of problems, from scientific inference and decision-making to ethical reasoning and even these philosophical questions about the very nature of knowledge.
Yeah, it's definitely changed my whole perspective on what probability is all about. It's not just about gambling or predicting the weather. It's a fundamental way of thinking about the world.
Exactly. And Jaynes really challenges us to be more conscious of the assumptions that we make, the information that we use, and the limitations of our knowledge. He calls for this more rigorous, more principled approach to reasoning based on the solid foundation of probability theory.
It's a call to be more thoughtful, more critical, and more honest with our thinking, and ultimately to embrace the power of probability as a tool for understanding this crazy, complex world around us.
Well said. I think that's a great note to end on. And if you're interested in learning more about this fascinating field, we encourage you to check out Jaynes' book and many other resources that are available online.
This has been an incredible journey. I feel like we've just scratched the surface of this vast and exciting world of knowledge. And who knows, maybe one day we'll be able to build machines that can actually think as logically and creatively as we can, all thanks to the power of probability theory.
That's the dream. And with the rapid advances in AI, it may be closer than we think.
Well, until next time, keep those brain cells firing, stay curious, and never stop exploring.